let's get started now on lecture number 20. In our previous lecture, we talked about electric potential. We found the relationship between electric potential and electric field. This is a general form. This is what we use if electric field is a constant. We figured out how to find electric field if we knew our potential for a particular coordinate systems. We thought about this equation and it gave us some relationships between electric potential and electric field. So potential is constant if the path is perpendicular to the field. Potential changes if the path is parallel to the field, and electric field points towards lower potential. We'll start this lecture by looking at the electric potential in the vicinity of a conductor in electrostatic equilibrium, just like we found the electric field of a conductor in electrostatic equilibrium. So let's get started. We'd like to find the electric potential both inside and outside. Let's remind ourselves of what we know about the electric field. So we'll say reminder. The electric field inside a conductor in electrostatic equilibrium is equal to 0 everywhere inside. So that's something that we know. We also know that the electric field has a magnitude of sigma over epsilon naught. Sigma is our surface area charge density. Epsilon naught is the permittivity of free space. And the direction is perpendicular to the surface, and this is the electric field just outside the conductor. We used Gauss's law to show that that was true. So let's start now and figure out the electric potential, and let's start with inside the conductor. So somewhere inside our oddly shaped conductor here. So let's start with our definition of electric potential. Delta V is minus the integral of electric field over the path taken. So let's draw our path in this problem. Let's say our path starts here, curves along, and ends here. We'll take some very general path. So this is S, our path. ds is a small element of that path. We can identify that. So it's a small little bit. It does have a direction, so we'll draw it with an arrow. So now let's fill in what we said we knew about the electric field inside of a conductor. We know that this is equal to 0 because the electric field inside a conductor in electrostatic equilibrium is always 0. So this is minus the integral of 0 dot ds. This is just 0. So what this result tells us is that the net change, delta V, is equal to 0 inside the conductor. Delta V equals 0 inside. What does it mean that delta V is 0? It means that the change is 0. That means V doesn't change. So the resulting conclusion is that V, our electric potential, is constant everywhere inside the conductor. This is sort of an interesting result. Electric field is 0, but our potential doesn't have to be 0. The change has to be 0, but the potential itself doesn't have to be 0. That's pretty interesting. Okay, now let's look at outside the conductor. So outside next. So for outside the conductor, just outside, let's look on the surface. So we'll start with our equation. Delta V is equal to negative the integral E dot ds. S again is our path, so let's draw a path which is on the surface. So let's start, say right here, this will be our initial point. And then our path will take us along the surface to some final point, let's say over here. So this is S, our path. ds is our small piece of a path. And let's make sure it's clear that our path S is all along the surface. sure the ink shows up from my pen. Okay, hopefully that's nice and clear now in your video. So there's our path S, there's our little piece of path that's called ds, our element of path, if you will. So as we try and figure out our delta V, let's think about the directions here. Our electric field is perpendicular to the surface. Our path element is parallel to the surface. That means that our electric field must be perpendicular to our path. So if we do our scalar product, delta V is minus the integral of the magnitude of V times the magnitude of ds times the cosine of the angle between them. That would be the cosine of 90 degrees because it's perpendicular, and we get 0. Okay, that's interesting too. So that tells us that delta V equals 0 on the surface. That means that the change is 0, so the V must be constant. V is constant everywhere on the surface. And then because the surface touches the inside, the V inside equals the V on the surface. So our big conclusion here is that the entire conductor is at the same potential. And when the entire conductor is at the same potential, sometimes we say that the conductor is an equipotential for equal potential. Okay, so this is for a general shaped conductor. Let's restrict ourselves now to a spherical conductor, and let's find the potential outside and inside a spherical conductor. We did that for the electric field around a spherical conductor. Now we'll look at electric potential. So here's our question. What is the potential associated with a spherical conductor in electrostatic equilibrium? It has net charge Q and radius r, and draw a graph of the potential. So we'd like to find the potential in outside the conductor, at the surface of the conductor, and inside the conductor. Once we figure all those things out, we'll draw a graph. So let's start with outside. So we're going to ask, what is the potential at some distance greater than the radius of the sphere? So there's my center. Here is the radius of the sphere. So this is r equal to the radius. I'm trying to find the potential outside, so for this value of r out here. So here's my outside. We'll start with our equation. Delta V is minus the integral of E dot ds equals. So let's think about what we have here. Our electric field is a vector. We know it points radially outwards. Radially out of a positive, radially into a negative. So our electric field only depends on the r direction. So the r direction, so in and out direction, is the important one. So E dot ds will be the same as E times dr. Okay, so if the electric field is parallel to the path, we get E times dr. We know that the electric field outside of a conductor is kq over r squared. Take our constants out front. K is our Coulomb's constant, that comes out front. Inside the integral of 1 over r squared dr. This is an integral I expect you know how to do. The integral of 1 over r squared is minus 1 over r. So that's minus kq times minus 1 over r. Minus times a minus gives us a plus. and it says that V, our potential outside the sphere, is equal to K times Q over R. In this result here, we recognize that we may take a reference point that if R equals infinity, the potential would be zero. You'll see this often written in the books. So whenever you see the words for reference, you may take the potential at a very far distance to be zero. When you see that wording, it means you can use the equation V is KQ over R. Okay, so there's outside the sphere. What about on the surface? That's V of R. Okay, so that's the one we'd like to do next. So what we can do here is we can plug in R equals the radius of the sphere. So V at R equals K times Q over the radius of the surface. That one was pretty straightforward. Last, we have inside. This one's also going to be pretty straightforward. So that's V at R less than R. So that's going to be some point here. So here's where we'll remember what we just figured out, that the entire conductor is an equipotential. It's all at the same potential. So the potential inside is the same as the potential on the surface. So V inside the sphere is equal to the potential at the surface of the sphere equals KQ over R. Okay, so that's finding the potential outside at the surface and inside. Next, we're asked to graph the potential. So let's think of the different places. So let's start with inside. So that's for R less than capital R. Inside, the potential always has value KQ over R. That's a constant value. Okay, so here's our inside bit. We can mark the value here on our axis because it is useful to know what that is. Once we get outside, the potential falls off as 1 over R. So it will die away as we get further away. So this is outside. Out here, V equals KQ over R. So as R gets very big, V will go to 0, which matches our reference point. We might want to compare this with our electric field graph. So the electric field is a function of distance from the sphere. Remember, inside the sphere, the electric field was 0. Then at the surface, it jumped to KQ over R squared. And then it fell off as 1 over R squared. So it's deeper falling off. Okay, so for comparison, the graphs, they have some similarities, but they're not exactly the same. One kind of major thing to recognize is that if our electric field is 0, it doesn't mean our potential is 0. It means our potential is constant. Okay, let's do a numerical example. Let's say we have a Van de Graaff generator. Those things are typically charged to about 50,000 volts, and they typically have a radius of about 20 centimeters. They're close to spherical. Can we figure out what is the charge on the surface of our Van de Graaff machine? So we know that our potential is 50,000 volts. The radius is 0.20 meters. And we'd like to know what is the charge on the surface. We know that if it's an electrostatic equilibrium, all the charge is on the surface. We know that V is equal to K times Q over R. We're trying to solve for Q. So Q is going to be V times R divided by K. 50,000 volts. times R, 0.2 meters, divided by K, 8.99, times 10 to the 9 Newton meters squared over Coulomb squared. We get that the charge on the surface of the Van de Graaff is 1.11 times 10 to the minus 6 coulombs, or 1.11 microcoulombs.